every second, a galaxy twice the size of our own drifts 110 kilometres closer. A trillion stars and a dark matter halo wider than the Milky Way itself, falling toward us without pause. In 1912, Vesto Slipher recorded its blueshift at Lowell Observatory, years before anyone even knew Andromeda was a galaxy. It is not slowing. It is not veering. The Hubble Space Telescope confirmed the trajectory is nearly head-on. For a century, one question refused to resolve. What actually happens when two galaxies collide? Then the simulations returned their answer. Not a single star will touch. The collision will be total, and the damage zero. Tonight, we trace the science, witness the forces reshaping both galaxies, and follow the fate of one star caught in the middle. If you enjoy the journey, subscribe, and a like genuinely helps. The fall has already begun. Let us meet what is coming. Right now, at this moment, the distance between the Milky Way and the Andromeda galaxy is shrinking. Not slowly, not occasionally, continuously, at roughly 110 kilometres every single second. That is nearly 400,000 kilometres every hour, closed silently, invisibly, across a gap that has been narrowing for billions of years. The distance still remaining is enormous. Roughly 2.5 million light-years separate the two galaxies, a number so large that the light arriving from Andromeda tonight left its stars before our species existed. And yet, that distance is not what it was a year ago, or a century ago, or 1,000,000 years ago. It contracts without pause, and it does not care whether anyone is watching. We know this because of a single, quiet observation made over a century ago. In 1912, an astronomer named Vesto Slipher was working at Lowell Observatory in Flagstaff, Arizona. He had turned the observatory's spectrograph toward the Andromeda Nebula, which at the time was believed to be exactly that, a nebula. A cloud of gas somewhere within our own galaxy, unremarkable except for its faint, elongated glow. Slipher was measuring its light, splitting it into a spectrum, looking for the telltale signatures of motion. What he found was a blueshift, a compression of light waves indicating that the object was moving toward us, not away. This was unusual. Among the roughly 40 nebulae whose velocities Slipher would eventually measure over the following years, almost all were receding. Almost all showed a redshift, their light stretched longer as they moved away, a pattern that would later become one of the first clues toward the discovery that the universe itself is expanding. Against that sea of retreat, Andromeda stood out. It was approaching. And it was doing so at a speed that Slipher initially estimated at roughly 300 kilometers per second, a figure later refined downward, but the direction never changed. In a universe where nearly everything is flying apart, Andromeda is falling toward us. The reason though Slipher could not have known it at the time is that the Milky Way and Andromeda are gravitationally bound to each other within a small family of galaxies called the local group. They are close enough and massive enough that their mutual gravity overwhelms the expansion of space between them. The universe pulls everything else apart. These two, it pulls together. What made this measurement so quietly extraordinary was not just its result, but its timing. Slipher had detected the blueshift years before anyone understood what Andromeda actually was. He had measured the approach of something whose true nature, its size, its distance, its staggering significance, would not become clear for another decade. And here is where the scale of the problem begins to sharpen. The Milky Way is not small. Its disk spans roughly 100,000 light-years from edge to edge, containing somewhere between 100 billion and 400 billion stars. It is, by any reasonable measure, immense. But Andromeda is larger. Its disk stretches across approximately 220,000 light-years. It holds an estimated 1 trillion stars. Its total stellar mass is roughly double that of our galaxy. This is not a collision between equals. The Milky Way is the smaller of the two, and the object bearing down on it is the single largest galaxy in our neighbourhood of the universe. The timeline for their meeting sits at approximately 4.5 billion years from now. That sounds safely distant until you hold it alongside another number, the current age of the Earth, which is also roughly 4.5 billion years. The time remaining before the collision is no greater than the time our planet has already existed. Everything that has ever lived, every ocean that has formed, every continent that has drifted, all of that fits inside the same window of time that now separates us from what is coming. And it is coming. The trajectory is not a projection or a best guess. It is a measured certainty, confirmed by instruments operating a century apart. The fall toward Andromeda is the oldest motion we have ever recorded from beyond the Milky Way, and it has not wavered since the day it was first seen. But in 1912, none of that weight was yet apparent, because in 1912 no one knew that Andromeda was a galaxy at all. For most of human history, the smudge of light in the constellation that bears its name was assumed to be something local. A cloud of luminous gas, perhaps. A nearby curiosity within the boundaries of the Milky Way. The idea that it might be a separate system, an entirely independent collection of billions of stars, separated from us by an almost incomprehensible gulf of empty space, was, to most astronomers, unnecessary. The Milky Way was already vast. Why would there need to be anything beyond it? The question came to a head in 1920, during what has since become known as the Great Debate. Two astronomers, Harlow Shapley and Heber Curtis, publicly argued opposing positions before the National Academy of Sciences in Washington. Shapley contended that the Milky Way was the entirety of the universe. The spiral nebulae, including Andromeda, were local features within it. Curtis disagreed. He believed the spiral nebulae were distant, independent systems, island universes, as they were sometimes called, each one a galaxy in its own right. His evidence was shrewd for its time. He had observed individual novae in Andromeda that appeared far fainter than similar explosions closer to home. If Andromeda were merely a nearby feature of the Milky Way, those novae should have been brighter. Their dimness implied a staggering distance, one that only made sense if Andromeda existed far beyond the boundaries of our own galaxy. The debate ended without a clear resolution. Both men had made compelling arguments, and the observational evidence available in 1920 was simply not precise enough to settle the matter. It would take a different astronomer, a different telescope, and a different kind of star to close the question. Edwin Hubble arrived at that answer in 1924, working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, at the time the most powerful telescope on Earth. Hubble identified a particular type of star within Andromeda, Cepheid variables. These are stars that pulse in brightness with a regular, predictable rhythm, and their importance lies in a relationship discovered years earlier by Henrietta Leavitt. Leavitt, working at Harvard College Observatory, had studied Cepheid variables in the Small Magellanic Cloud and found something remarkable. The period of a Cepheid's pulsation, how long it takes to brighten and dim, is directly related to its true luminosity. A Cepheid that pulses slowly is intrinsically brighter than one that pulses quickly. This was not a minor observation. It was the key to measuring the universe. If you could observe a Cepheid's pulsation period, you could calculate its intrinsic brightness. Compare that to how bright it appeared from Earth, and you could work out how far away it was. The relationship became known as the period luminosity law, and its influence is difficult to overstate. It transformed Cepheids into cosmic measuring rods, standard candles that could reveal distances no other method could reach. Leavitt's contribution would go on to underpin the entire modern cosmic distance ladder, a framework still used today to calibrate distances across the observable universe. But in the early 1920s, its most immediate consequence was more personal to our story. Hubble found Cepheids in Andromeda. He measured their pulsation periods. He applied Leavitt's law, and the distance he calculated, roughly 900,000 light-years, later revised upward to well over 2 million, was far beyond anything that could possibly exist within the Milky Way. The result reached Shapley by letter. By one account, he looked at it and said that it was the letter that had destroyed his universe. Whether or not those were his exact words, the sentiment was accurate. The Milky Way was not everything. Andromeda was not a nebula. It was not a cloud of gas inside our galaxy. It was a galaxy of its own, separated from us by a void so deep that its light had been travelling for millions of years before reaching Hubble's photographic plates. In a single result, the known universe expanded beyond recognition. The Milky Way, which had been everything, became one galaxy among what would eventually be understood as hundreds of billions. And the object that Slipher had found drifting toward us 12 years earlier, that faint, blue-shifted smudge, was suddenly not a wisp of gas falling inwards. It was something immeasurably larger, immeasurably heavier, and immeasurably more consequential. A galaxy containing 1 trillion stars heading directly for ours. Except that directly was for a long time an assumption. Slipher's blueshift told astronomers that Andromeda was moving toward the Milky Way. Hubble's distance measurement told them how far apart the two galaxies were, but there was a piece of the puzzle that neither observation could provide, and without it, the nature of the encounter remained genuinely uncertain. The problem was sideways motion. Slipher had measured what is called the radial velocity, the component of Andromeda's movement along the line of sight, toward or away from us. That number was well established. But galaxies do not move in only one dimension. Andromeda could also be drifting sideways, perpendicular to our line of sight, and that component, known as the transverse velocity, was completely unknown for most of the 20th century. This mattered enormously. If the sideways drift were large enough, the two galaxies might pass each other at an angle, a glancing blow that would distort both systems, but never produce a true merger. If it were larger still, they might miss each other entirely, swinging past on a wide arc and drifting apart again. Only if the transverse velocity were small, truly small relative to the approach speed, would the collision be head-on. 3 very different futures, and no way to distinguish between them. The difficulty was technical, and it was severe. At a distance of 2.5 million light-years, even a substantial sideways velocity produces an angular motion on the sky so small that it is measured in micro arcseconds per year. To put that in perspective, a micro arcsecond is roughly the angle subtended by a coin on the surface of the Moon as seen from Earth. Detecting that kind of shift requires not only extraordinary precision, but years of patient observation, long enough for the motion to accumulate into something measurable. It took until 2012 for the answer to arrive. Roland van der Marel and Sangmo Tony Sohn, working at the Space Telescope Science Institute, used the Hubble Space Telescope to track the positions of stars within Andromeda against a grid of distant background galaxies. Those background galaxies, billions of light years away, are so remote that their own apparent motion is essentially zero. They form a fixed reference frame against which Andromeda's drift can be measured. Over a baseline of 5 to 7 years, van der Marel and Sohn detected the shift. Andromeda's transverse velocity came in at approximately 17 kilometres per second. 17, against an approach speed of 110. The sideways drift was barely a fraction of the inward fall. The collision would not be a glancing blow. It would not be a miss. It would be very nearly head-on. Two galaxies meeting face to face across 2.5 million light years of empty space. The result did not stop there. Van der Marel's paper also modelled the future trajectory of a third galaxy, the Triangulum galaxy, Messier 33, the third largest member of the local group. Triangulum orbits in the gravitational neighbourhood of Andromeda, and the simulations showed its fate was tangled with the merger. Depending on the precise orbital parameters, Triangulum might be absorbed during the collision, flung outward on a wide arc, or drawn in afterward as the merged system settles. 3 galaxies, not 2, are part of this story. Then, in 2019, independent confirmation arrived from an entirely different instrument. ESA's Gaia spacecraft, designed to map the positions and motions of over 1 billion stars, measured proper motions in the outer regions of Andromeda and returned a transverse velocity consistent with the Hubble result. 2 telescopes, 2 methods, 2 teams, the same conclusion. The collision is not a hypothesis. It is not a likely outcome. It is a trajectory measured to a precision that leaves no room for an alternative. Somewhere in the next 4.5 billion years, over 1 trillion stars belonging to 2 separate galaxies will occupy the same volume of space. The fall has been measured, the angle confirmed, and the outcome placed beyond reasonable doubt. What no one appreciated for most of that century of measurement, what Slipher could not have known in 1912, what Hubble could not have guessed in 1924, what even van der Marel might not have emphasised in his 2012 paper, is that the Milky Way has been through this before. Not once, many times. The evidence is not written in telescopic images of distant galaxies. It is written in our own. Buried inside the Milky Way, in the orbits of its stars, in their chemical compositions, in the streams and loops and anomalies that thread through its halo, is a forensic record of every galaxy it has ever consumed. The field that reads this record is sometimes called galactic archaeology, and over the past decade, it has transformed our understanding of what the Milky Way actually is. The breakthrough came from ESA's Gaia spacecraft. In 2018, a team led by Amina Helmi at the University of Groningen published a discovery in Nature that reshaped the Milky Way's biography. Using Gaia's precise measurements of stellar positions and velocities, Helmi identified a large population of stars in the inner halo whose orbits were strikingly different from the native disk population. These stars followed highly elongated eccentric paths, and when their velocities were plotted in a certain way, they formed an unmistakable elongated shape, a sausage. the name stuck. The Gaia sausage, more formally Gaia Enceladus, was the remnant of a substantial dwarf galaxy that had collided with the early Milky Way roughly 8 to 11 billion years ago. The dwarf galaxy no longer existed as an independent structure. It had been absorbed entirely. But its stars were still there, still following their original orbits, still carrying the chemical fingerprints of their birth galaxy. Ghosts with trajectories. The collision had not been gentle. It had delivered billions of solar masses of new material into the Milky Way's inner halo. And there is strong evidence that the impact helped reshape the early disk itself, thickening it, heating it, scattering stars that had previously orbited in calm circular paths into more disturbed configurations. The Milky Way we see today, its thick disk, its layered halo, its complex kinematic structure, was partly built by this single ancient merger. That was not the oldest star. In 2020, Diederik Kryson at Heidelberg University and his collaborators published a reconstruction of the Milky Way's full merger history using a combination of observational data and the E-mosaic simulations. Among their findings was a merger they named Kraken, a galaxy that had been absorbed roughly 11 billion years ago, when the Milky Way was still young and significantly smaller. Kraken was not a minor acquisition. At the time of the collision, it carried roughly a quarter of the Milky Way's own mass. It was, proportionally, one of the most significant events in our galaxy's early life, and its remnants are embedded deep in the inner galaxy, where they are hardest to disentangle from native stars. Kreuzen's team identified its traces through the chemical abundance patterns and kinematics of globular clusters, ancient, dense balls of stars that survived the merger intact and still carry the chemical signature of the galaxy that formed them. And then there is the one that is happening right now. The Sagittarius dwarf elliptical galaxy was discovered in 1994 by Rodrigo Ibata, Gerard Gilmore, and Mike Irwin. It sits on the far side of the galactic centre from Earth, and it is being destroyed. Over billions of years, it has passed through the Milky Way's disk multiple times, and each passage has stripped away more of its stars. Today, its tidal streams, long arcs of liberated stars, wrap around the entire galaxy like ribbons pulled loose from a spool. Research published in Nature Astronomy in 2020 by Tomás Ruiz Lara and collaborators at the Instituto de Astrofísica de Canarias found something remarkable in these passages. Each time the Sagittarius dwarf plunged through the disk, it appears to have triggered a burst of star formation in the Milky Way. One of those bursts aligns closely with the estimated age of the Sun. It is possible, not proven, but consistent with the data, that our own star owes its existence to the gravitational disruption caused by a galaxy that is now being torn apart. These are not isolated incidents. The Helmy streams, identified by Amina Helmy in 1999, are the remnant of yet another absorbed dwarf galaxy. Its stars still clustered in velocity space 5 to 8 billion years after the merger. Sequoia, identified through Gaia kinematics, contributed stars to the retrograde halo roughly 9 billion years ago. The Milky Way's outskirts are littered with the remains of galaxies it has pulled in and dissolved, their stars redistributed, their identities erased, their matter folded into our own. Even now, the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere, are interacting gravitationally with the Milky Way and are likely to be absorbed in the distant future. The feeding has never stopped. The Milky Way is not a passive structure waiting for its first collision. It is a cannibal with a record stretching back over 11 billion years. It has consumed dwarf galaxies whole, absorbed their stars, triggered waves of new creation from the violence of each encounter, and carried the evidence in its own body ever since. But every previous meal was smaller. Every absorbed galaxy was a fraction of the Milky Way's mass, a dwarf swallowed by a giant. Andromeda is not a dwarf. Andromeda is larger, and for the first time in its history, the Milky Way is falling towards something that will not be consumed. It is falling towards something that may, in the end, consume it. So here is a collision involving over 1 trillion stars on one side and up to 400 billion on the other, closing at 110 kilometres per second across a gap of 2.5 million light years. And the claim at the heart of this story is that absolutely nothing will happen. That sounds impossible. It sounds like the kind of thing someone says to be provocative rather than accurate. But it is accurate, and the reason is one of the most quietly staggering facts about the universe we live in. Space, even within a galaxy, is overwhelmingly empty. The nearest star to the Sun is Proxima Centauri, sitting at a distance of roughly 4.24 light years. That is about 40 trillion kilometres. The Sun itself is large by human standards, roughly 1.4 million kilometres across. But against a gap of 40 trillion kilometres, it is a speck. To feel the true scale of that emptiness, imagine shrinking the Sun down to a grain of sand, roughly a millimetre wide. At that scale, Proxima Centauri would be another grain of sand, sitting approximately 6 kilometres away. Between those two grains, 6 kilometres of nothing. No matter, no obstacle, no possibility of contact. Just distance. And that is the closest pair. Most stars in the Milky Way are separated by far greater margins. The galaxy contains somewhere between 100 billion and 400 billion stars spread across a disk roughly 100,000 light-years in diameter, and the ratio of empty space to actual stellar matter is difficult to express without it sounding absurd. If you were to fire a projectile in a random direction through the Milky Way's disk, from one edge to the other, a journey of 100,000 light years, the probability of that projectile striking a star along the way is vanishingly small. The galaxy is not a crowded room. It is a vast, dark hall with a few scattered grains of light separated by distances that dwarf the objects themselves. This is why the word collision, applied to galaxies, is one of the most misleading terms in astronomy. It describes something gravitationally real, but physically untrue. When two galaxies merge, their stars do not collide, they pass through each other. Galaxy merger simulations have confirmed this repeatedly. John Dubinsky at the University of Toronto and Lars Hernquist at Harvard, among others, have modelled the gravitational dynamics of major mergers in extraordinary detail, tracking the trajectories of millions of simulated stellar particles as two galaxies fall together, pass through each other, swing back, and eventually coalesce. In every simulation, the result is the same. Individual stars sail past one another with enormous separations. The probability of any two stars physically touching during a major galaxy merger is, for all practical purposes, 0, not unlikely, not rare, effectively impossible. Even in the densest regions of a galaxy, the core, where stars are packed more tightly than anywhere else, separations still measure in light weeks to light months. These are the closest quarters a galaxy offers, and they are still incomprehensibly vast by any human standard. There is one environment in the Milky Way where stars do come close enough to affect each other directly, and it is worth pausing on. Not because it contradicts the point, but because it sharpens it. Globular clusters are ancient, spherical collections of stars bound tightly together by their own gravity. Some contain hundreds of thousands of stars, packed into a volume only a few dozen light-years across. In these cramped environments, close gravitational encounters between stars are not unusual. Binary star systems get disrupted. Stars capture new gravitational partners. A phenomenon called blue straggler formation occurs, older stars appearing to rejuvenate through mass transfer or mergers with close neighbours. In globular clusters, stars genuinely interact, but even here, physical collisions, two stellar surfaces actually touching, remain rare events. What happens in globular clusters is gravitational. Stars altering each other's orbits, exchanging energy, occasionally merging through slow spirals rather than direct impact. If the densest stellar environments in the entire galaxy can barely produce a physical collision, then a galaxy merger, where the average star has light years of empty space on every side, has no chance at all. The merger of the Milky Way and Andromeda will be total. The gravitational disruption will be immense. The shapes of both galaxies will be torn apart, their spiral arms unwound, their stars flung onto new orbits in a combined system that resembles neither parent. But through all of it, through every pass, every tidal disruption, every billion years of gravitational reshaping, the stars themselves will drift past one another like ships in an ocean so wide that no two hulls will ever touch. The system merges. The objects within it do not. That is the paradox at the heart of this collision. It is real, it is inevitable, it will reshape the structure of our galaxy beyond recognition, and at the level of individual stars, it will be as though nothing happened at all. But if the stars will not touch, something must drive the merger. Something must reach across 2.5 million light-years, pull both galaxies off their paths, and reshape them into a single system. The force responsible is gravity, and the mass generating most of that gravity is something we cannot see. Both the Milky Way and Andromeda are embedded in halos of dark matter that extend far beyond the edges of their visible disks. The Milky Way's luminous stars stretch across roughly 100,000 light-years, but its dark matter halo, a vast, diffuse sphere of gravitationally influential material, may reach over 300,000 light-years from the galactic centre, perhaps further. Andromeda's halo is at least as large. These are not thin shells. They are enormous, three-dimensional structures that contain the majority of each galaxy's total mass. The stars, the gas, the dust, everything the eye can see or a telescope can photograph, accounts for only a fraction of what is actually there. The rest is dark matter, detectable only by its gravitational influence on everything around it. The evidence for these halos was built slowly, but one contribution stands above most. In the 1970s, Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies, including Andromeda itself, and found something that did not fit. Stars in the outer regions of these galaxies were orbiting far too quickly. If the only mass present were the visible matter, stars and gas, those outer stars should have been moving more slowly, their orbits dictated by a declining gravitational pull. Instead, the rotation curves stayed flat. The orbital speeds held steady far beyond the visible disk, implying that enormous amounts of unseen mass extended well past the galaxy's luminous boundary. That unseen mass was dark matter, and Rubin's observations became one of the strongest pillars supporting its existence. This is what will make first contact. Long before the visible disks of the Milky Way and Andromeda draw near each other, their dark matter halos will begin to overlap. Depending on how far each halo truly extends, this may have already begun. Two invisible spheres of gravitational influence, reaching toward each other across the void, starting to entangle. The merger, in its deepest sense, does not begin with light or fire. It begins in silence, with matter that no instrument has ever directly observed, reshaping the gravitational landscape that everything else must follow. There is something worth sitting with in that thought. The single most consequential event in our galaxy's future, an event that will reshape the structure of hundreds of billions of stars, will begin with something invisible, driven by something we have never touched, never bottled, never isolated in a laboratory. We know dark matter exists, or because we can see what it does. We do not know what it is. Dark matter is collisionless. Unlike gas, it does not slam together, heat up, or radiate energy. It passes through itself as though the other mass were not there. But its gravity is real, and as the two halos interpenetrate, the gravitational potential of the combined system shifts. Stars that once orbited in stable patterns find their paths subtly altered. The outermost stars and satellite galaxies are the first to feel it, drawn slightly off course, their orbits nudged by the growing presence of a second, massive gravitational field moving through their space. We have seen this separation of behaviours directly. In a galaxy cluster collision, known as the Bullet Cluster, observed roughly 3.8 billion light-years away, two clusters of galaxies pass through each other at enormous speed. The hot intergalactic gas, glowing in X-ray light and mapped by the X-ray Observatory, slowed and piled up at the point of collision, heated to hundreds of millions of degrees by the impact. But the dark matter, traced indirectly through gravitational lensing, the bending of light from even more distant galaxies behind the cluster, passed straight through without interacting. The two components separated cleanly, visible on opposite sides of the collision, each behaving according to its nature. It was one of the most striking confirmations that dark matter is real, that it dominates the mass of cosmic structures, and that it behaves in a fundamentally different way from the matter we are made of. In the Milky Way Andromeda merger, the same separation will play out. Dark matter will slide through dark matter. Gas will not. The first visible signs of the merger will be subtle. Tidal distortions in the outermost regions of both disks. Faint warps, streams of stars pulled gently outward by the approaching gravitational fields. Bridges of material may form between the two galaxies as their halos draw closer. But the early stages will be quiet. The drama, when it arrives, will come from something far thinner and far more fragile than stars. The space between stars is not truly empty. Threaded through both galaxies is a thin but real substance, the interstellar medium. It is made of gas, dust, and molecules, distributed in vast clouds between the stars. Most of it is hydrogen in various forms. Hot and ionized near energetic stars, cold and atomic in more diffuse regions, and in the densest pockets, molecular. Hydrogen atoms paired together into molecules, chilled to just a few degrees above absolute zero. These molecular clouds are the nurseries of star formation. Left undisturbed, they can drift for millions of years in a delicate equilibrium between their own gravity pulling inward and their internal pressure pushing out. They are stable, patient, and dark, invisible except at infrared and radio wavelengths. But they are also fragile, and they are about to be shaken. When the interstellar media of two galaxies meet, the gas does what stars do not. it collides. Unlike dark matter, which is collisionless, and unlike stars which are separated by distances too vast for contact, gas clouds interact directly. As the two media compress against each other, shock waves ripple through the gas, propagating at speeds of hundreds of kilometres per second. Temperatures spike, densities rise. Molecular clouds that might have drifted in equilibrium for millions of years are suddenly squeezed past their stability threshold. The balance between gravity and pressure tips. The clouds fragment, contract, and begin to collapse. This is the trigger for star formation. And during a major merger, it happens on a scale that transforms the entire system. There is an empirical relationship, described by the Kennicutt-Schmidt law, that links the surface density of gas in a galaxy to its rate of star formation. In a normal, undisturbed spiral galaxy, the gas sites at moderate densities and forms stars at a steady, measured pace. But when a merger compresses that gas, when shock waves drive the density across critical thresholds, the star formation rate accelerates dramatically. The law predicts it, and observations confirm it. Merging galaxies form stars at rates far beyond anything a spiral galaxy achieves in isolation. We do not need to imagine what this looks like. We can see it happening. Roughly 45 million light-years away, in the constellation Corvus, two spiral galaxies are in the midst of a collision. They are called the antennae galaxies, named for the long sweeping tidal tails of stars that extend outward from the merging cores like the antennae of an insect. In the overlap region, where the interstellar media of both galaxies have met and compressed, the result is spectacular. Thousands of new star clusters are forming simultaneously, some so massive and so tightly bound that they are expected to survive as globular clusters for billions of years. The antennae are not just forming stars, they are building structures that will endure long after the merger itself is a distant memory. At an earlier stage of the same process, roughly 290 million light-years away, the Mice galaxies offer a different view. Two galaxies, their long tidal tails already flung outward, earning them the name for their resemblance to two mice trailing their tails, are in the opening phase of a merger. The gas compression is beginning, the structural distortion is visible, but the most violent starburst has not yet arrived. The mice show what the early stages look like. The moment before the interstellar media truly collide, when the gravitational damage is mounting, but the creative explosion has yet to begin. The mice are a preview. The antennae are the main event, and together they form a timeline, a sequence of snapshots that shows, in real galaxies observed at real distances, exactly what happens when two spirals fall together. When the Milky Way's interstellar medium meets Andromeda's, the same physics will apply. Gas will compress. Molecular clouds will collapse. New stars will ignite in numbers that dwarf anything our galaxy produces today. The stars that existed before the merger will sail past each other untouched, but the gas between them will collide violently, and from that violence, an entirely new generation of stars will be born. It is one of the strangest truths of galactic evolution. Destruction and creation are not opposites. In a galaxy merger, they are the same event. The scale of that creation is difficult to overstate. In a normal spiral galaxy, like the Milky Way, new stars form at a modest, sustainable rate. A few solar masses of material converted into new stars each year, scattered across the disk, wherever conditions allow molecular clouds to collapse. It is a slow, quiet process. The galaxy ticks over. Stars are born, stars die, and the balance holds across billions of years. During the peak of a major merger, that balance shatters. Star formation rates can surge to 10 times the normal rate, sometimes higher. Across the overlap regions where compressed gas has piled up, molecular clouds collapse in cascades. Massive new star clusters form, not gently and not one at a time, but in violent, simultaneous bursts. Some of these clusters contain hundreds of thousands of stars bound tightly together by their shared gravity, forged in a single wave of creation that would be impossible under normal galactic conditions. Many of the new stars born in this frenzy are enormous. Stellar mass is not evenly distributed when clouds collapse. Some fragments gather far more material than others, producing stars 10, 20, 50 times the mass of the Sun. These giants are dazzling. They burn with a ferocity that makes them among the brightest objects in the galaxy. But that brightness comes at a cost. A star 50 times the mass of the Sun does not live 50 times shorter. It lives millions of times shorter. Where the Sun will burn steadily for roughly 10 billion years, a massive star might exhaust its fuel in 3 or 4 million. It burns fast, burns hot, and then it dies, often violently in a supernova explosion that briefly outshines the entire galaxy around it. During the starburst phase of a merger, supernovae are not rare events. They are a drumbeat. Thousands of massive stars, born almost simultaneously in the compressed gas, reach the end of their lives within a few million years of each other. The result is a sustained barrage of explosions that pumps enormous amounts of energy back into the surrounding gas, heating it, scattering it, driving powerful winds that can push material out of the galaxy entirely. And here lies the starburst's own contradiction. The very process that creates new stars also begins to destroy the conditions that allowed them to form. Supernovae heat the remaining gas. Stellar winds from massive young stars strip material from nearby clouds. The cold, dense molecular reservoirs that fueled the burst are consumed from within and eroded from without. Star formation does not sustain itself. It burns through its own fuel supply and then declines. The starburst, for all its fury, is temporary. This sequence, ignition, blaze, exhaustion, has been observed in galaxy after galaxy. Roughly 250 million light-years away, ARP 220 shows the process near its peak. It is a late-stage merger, the two original galactic nuclei still visible, but drawn so close together that they are separated by only a few thousand light-years. The system pours out energy, but not primarily in visible light. The intense star formation is buried behind thick curtains of dust, and that dust, heated by the starburst, re-radiates the energy at infrared wavelengths. ARP 220 belongs to a class of objects called ultraluminous infrared galaxies, systems that emit more energy in the infrared than in all other wavelengths combined. They are among the most luminous objects in the nearby universe, and nearly all of them are mergers. Researchers David Sanders and Mirabel proposed an evolutionary sequence for these systems. That merging spiral galaxies pass through a starburst phase, become ultraluminous infrared galaxies as dust obscures the activity, and eventually settle, once the gas is exhausted and the dust clears, into quiet elliptical galaxies. It is a life cycle driven entirely by the merger, and it places the future Milky Way Andromeda collision into a well-studied pattern. What will happen to our galaxy is not without precedent. It has happened before, elsewhere many times. The end of that sequence can be seen as well. NGC725. 2, sometimes called the Atoms for Peace galaxy, is a post-merger remnant roughly 220 million light-years away, its tidal debris is still visible. Faint shells and loops of stars thrown outward during the merger's most violent phase. But the starburst has faded. The galaxy is settling. Its shape is no longer spiral, but elliptical. Its stars orbiting in a diffuse, rounded cloud rather than a flat, rotating disk. It is what the Milky Way and Andromeda will eventually become. A quieter, older system. Its fires spent. Its structure permanently transformed. The process that astronomers call quenching, the shutting down of star formation after a merger, does not happen through a single mechanism. It is a convergence. The gas runs out. Supernovae heat what remains. And if the central supermassive black hole becomes active during the merger, accreting gas and releasing jets of energy, that too can drive remaining cold gas out of the galaxy or heat it beyond the point where it can collapse into new stars. The merger creates, and then the merger's consequences prevent further creation. The galaxy goes quiet. But the starburst is not the only drama unfolding at the heart of a merger. Something else is falling inward. Something far smaller, far denser, and far more consequential for the long-term future of the combined system. At the centre of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass of approximately 4 million times that of the Sun. We know its mass with remarkable precision because for decades, 2 independent teams have tracked the orbits of stars circling it. Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics both followed a star known as S2 as it completed a full orbit around the invisible centre, a loop that takes roughly 16 years and brings it within about 120 astronomical units of the black hole at its closest approach. Their measurements agreed, the mass was confirmed. In 2020, both shared the Nobel Prize in Physics for the work. 4 million solar masses sounds enormous, it is. But Andromeda's central black hole is in a different category entirely. Estimates place it between 100 and 230 million solar masses, roughly 25 to 50 times more massive than Sagittarius A star. It is one of the largest supermassive black holes in the local universe, and when the merger is complete, it will not simply coexist with the Milky Way's black hole, the two will fall toward each other. The process begins with dynamical friction. As the merged galaxy settles, each black hole moves through a dense field of surrounding stars. The gravitational tug of each black hole pulls stars toward it as it passes, creating a wake of slightly denser material behind it. That wake, in turn, exerts a gravitational drag, slowing the black hole, stealing its orbital energy, and causing it to spiral inward. Over hundreds of millions of years, the two black holes sink toward the centre of the merged system, drawing closer with each orbit. Eventually, they form a binary, 2 supermassive black holes orbiting each other at the heart of the new galaxy. Before they merge, both may actively accrete gas from their surroundings, producing a temporary phase where 2 active galactic nuclei shine simultaneously from the same system. Dual active nuclei have been observed in other merging galaxies. They are not theoretical. As the binary tightens, a long-standing puzzle in astrophysics emerges. Dynamical friction becomes less effective at close range, and there was concern for years that the 2 black holes might stall, unable to shed enough orbital energy to close the final distance, a problem known as the final parsec problem. More recent work has shown that interactions with surrounding stars and gas can bridge this gap, scattering stars that wander too close and extracting the energy needed to continue the in-spiral. When the two black holes finally coalesce, the event will release an extraordinary pulse of gravitational waves, ripples in the fabric of space-time itself. These waves will be at frequencies far below what LIGO or any ground-based detector can sense. They will, however, sit precisely in the detection range of LISA, a planned space-based gravitational wave observatory designed to observe the mergers of supermassive black holes across cosmic distances. The Milky Way Andromeda merger is exactly the kind of event LISA is being built to hear. There is a broader context to this. Across the universe, supermassive black hole mergers have been happening for billions of years. Every time two major galaxies collide, the same process plays out. The combined signal from all those mergers, accumulated over cosmic history, creates a faint gravitational wave background that permeates all of space. Pulsar timing arrays, projects like NanoGrav, have recently begun detecting evidence of this background by monitoring subtle timing variations in distant pulsars. The Milky Way Andromeda coalescence, from the perspective of observers in distant galaxies billions of years from now, will add its own ripple to that chorus. The merged black hole, hundreds of millions of solar masses, anchored at the centre of a new elliptical galaxy, will become the gravitational heart of everything that remains. A single, invisible anchor around which the stars of two former galaxies will orbit for trillions of years. All of this, the dark matter entanglement, the gas collisions, the starburst, the spiralling black holes, describes forces and structures operating at scales so vast that they can feel abstract. But there is a way to make the merger immediate, personal even. You can look up. On a clear dark night, away from city light, Andromeda is visible to the naked eye. It appears as a faint, elongated smudge in the constellation that shares its name. A soft blur of light that most people, if they notice it at all, might take for a wisp of cloud. It is the most distant object that most human beings will ever see without a telescope. What few people realise is how large it already is. The bright core, the part visible to the unaided eye, is only a fraction of the full galaxy. Its faint outer regions, captured in long exposure photographs, span roughly 6 times the diameter of the full moon. Andromeda is not a small, distant point. It is already an enormous presence in our sky, hidden only by its faintness. And it is growing as the gap between the two galaxies closes, 110 kilometres per second, year after year, millennium after millennium. Andromeda will brighten and expand across the sky. Slowly at first, imperceptibly over human lifetimes, but steadily over millions of years. If you could compress billions of years into minutes, you would watch a faint smudge swell into a great spiral, its arms reaching outward until they filled a significant portion of the visible sky, rivaling and then dwarfing the band of the Milky Way itself. NASA and the Space Telescope Science Institute have produced visualizations of this progression based on the orbital simulations and merger models. They show a sequence that is both beautiful and unsettling. In the early stages, Andromeda appears as a distinct spiral approaching from one side of the sky, 2 galaxies visible simultaneously, each holding its shape. Then, as the first close pass occurs, tidal forces begin to warp both disks. Stars are pulled into long streams. The familiar band of the Milky Way, that pale river of light that has arched over every human civilization, begins to distort, bending and twisting as gravitational forces redistribute stars across new orbits. During the active merger, the sky becomes something no living human has ever seen. Tidal tails sweep across the darkness. Bright knots of new star formation, ignited by the gas collisions, blaze in regions where the sky was once empty. The two galactic cores, still distinct, hang in the sky as luminous concentrations of light, drawing closer with each pass. It is chaotic, radiant, and entirely alien. After the merger settles, once the passes are complete, the starburst has faded, and the combined system has relaxed into a new shape. The sky changes one final time. The band of the Milky Way is gone. In its place is a diffuse, rounded glow, the light of an elliptical galaxy seen from the inside. Still beautiful, perhaps, in its own way, but unrecognizable. The sky of a galaxy that no longer carries either name. There is a weight to that. The Milky Way, as a distinct structure, has existed for over 13 billion years. It formed in the early universe, assembled itself through gravity, built its spiral arms, gathered its stars and gas into the disk we see today. It predates the Sun by roughly 8 billion years. It predates the Earth by 9. Every star that has ever shone in our sky, every constellation that has ever been named, every photon of starlight that has ever reached a human eye, all of it belongs to the Milky Way. When the merger is complete, that identity is gone. Not destroyed in the violent sense, nothing is annihilated, but dissolved. Absorbed into something new. Something that is neither the Milky Way nor Andromeda, but a third thing, with no history of its own, and the combined mass of both. In the language of galactic morphology, this is called a transformation. A shift from the spiral branch to the elliptical branch, permanent and irreversible. In simpler terms, it is the end of the galaxy we live in, not through catastrophe, but through merging. The Milky Way will not die. It will simply cease to be itself. But within that transformation, individual objects persist. Stars are not destroyed by the merger. Their orbits change dramatically and permanently. In a spiral galaxy, stars orbit in a relatively ordered fashion, mostly circular paths confined to a thin disk, all rotating in the same direction, like water swirling in a basin. After a major merger, that order is gone. The gravitational scattering of billions of close encounters between stars from two different galaxies randomizes the orbits. Stars no longer travel in neat circles within a flat plane. They move in elongated, tilted, chaotic paths that carry them above and below and through the center of the merged system in every direction. This is the kinematic signature of an elliptical galaxy. Not a rotating disk, but a swarm. Each star tracing its own independent orbit through a shared gravitational field. The stars themselves continue to burn, to age, to follow the physics of their own interiors. But the orderly galaxy they once belonged to has been replaced by something fundamentally different in structure, which raises a question far closer to home. What happens to the Sun? In 2008, T.J. Cox and Abraham Loeb at the Harvard Smithsonian Center for Astrophysics published a detailed study of exactly this question. Using N-body simulations of the Milky Way-Andromeda merger, they tracked the likely fate of a star at the Sun's position, roughly 26,000 light-years from the galactic center, embedded in the disk, through the full duration of the collision. The most likely outcome, with a probability of roughly 50%, is displacement. The solar system would be pushed outward to a larger galactic orbit, approximately 3 times its current distance from the center, by the gravitational reshuffling of the merger. It would not be destroyed, not disrupted, not stripped of its planets. The Sun would continue to burn. The Earth would continue to orbit. The solar system, as a self-contained gravitational unit, is robust enough to survive the passage of nearby stars without losing its structure. It would simply find itself in a different part of a much larger galaxy, orbiting a centre that no longer belongs to the Milky Way alone. A smaller probability, roughly 12%, places the solar system in temporary capture by Andromeda's remnant core during one of the merger's intermediate passes, before the two systems fully coalesce. And then there is the smallest but most striking possibility. Cox and Loeb's simulations gave a probability of roughly 2 to 3% that the solar system would be ejected entirely, flung out of the merged galaxy on an escape trajectory cast into intergalactic space. A star without a galaxy. Intergalactic stars are real. They have been detected in galaxy clusters through a faint glow of intracluster light, the combined luminance of billions of stars that were liberated from their parent galaxies during past mergers. They drift in the voids between galaxies, orbiting nothing, belonging to nothing. If the Sun were ejected, it would join them, a solitary point of light in a darkness that stretches for millions of light years in every direction. But none of these outcomes may matter, and this is the deepest irony of the entire story. The Milky Way Andromeda merger will reach its most dramatic phase in roughly 4.5 billion years. The Sun, independently, will exhaust the hydrogen fuel in its core in roughly 5 billion years. When that happens, the core will contract under its own gravity while the outer layers expand. The Sun will swell into a red giant, growing to perhaps 200 times its current diameter, brightening 1,000-fold, and almost certainly engulfing Mercury and Venus. Earth's fate in this scenario is marginal at best. Long before the Sun physically reaches our planet, its increasing luminosity will strip the atmosphere, boil the oceans, and sterilize the surface. Current models suggest Earth will become uninhabitable within roughly 1 billion years, well before the merger arrives in earnest. The two most dramatic events in our cosmic neighbourhood, the death of the Sun and the collision of our galaxy, will unfold within approximately the same billion-year window. They are unrelated in every physical sense, connected only by the coincidence of timing. But the implication is stark. By the time the Milky Way is torn apart, reshaped, and dissolved into something new, the Earth will already be gone. The oceans will have evaporated, the continents will have melted. Whatever life exists on this planet today will have no descendants to witness the sky change. The collision is real. The collision is inevitable. And it is, for anything alive on Earth right now, completely irrelevant. That is perhaps the strangest thing about it. An event of almost incomprehensible scale. 2 galaxies, 1 trillion stars, billions of years of gravitational drama, and it will unfold before an audience of no one, at least no one from here. What remains, when the passes are over and the gravitational fury has spent itself, is a galaxy that never existed before. It will be large, massive, roughly 1.5 trillion stars drawn from 2 separate spirals, now bound together in a single elliptical system. The spiral arms of both progenitors, those elegant, sweeping structures of gas and young stars, will be gone. Not hidden, not compressed, but genuinely destroyed. Spiral structure requires a rotating disk, and the merger will have dismantled both disks entirely. In their place will be a smooth, rounded cloud of stars, brighter at the centre, dimming gradually toward the edges, with no preferred plane of rotation and no grand pattern to its shape. Astronomers have informally named this future galaxy Milkdromeda. It is not a poetic name, but it is accurate. The Triangulum galaxy Messier 33, the third largest member of the local group, will likely follow. Orbital models suggest Triangulum may be drawn into the merged system during the collision or captured in the aftermath, adding its own 40 billion stars to the total. The local group, which today is defined by the gravitational balance between its two dominant spirals, will be reshaped around a single, enormous elliptical. Roughly 80 smaller galaxies that currently orbit in the group's gravitational well will find their dynamics altered. Some drawn closer, some scattered outwards, all responding to a centre of mass that has fundamentally changed. Inside Milkdromeda, the pace of creation will slow. The starburst will have consumed or expelled much of the available gas. The cold molecular clouds that once fueled steady star formation across both disks will be largely gone, used up in the burst, heated beyond recovery, or driven out by the combined force of supernova winds and the energy released by the central black hole. New stars will still form, but rarely and in diminishing numbers. The galaxy will age. Its stellar population will redden as the brightest, hottest stars burn out first and are not replaced. Over billions of years, Milkdromeda will become what astronomers call a red and dead elliptical, a system rich in old stars, poor in gas, and quiet in a way that neither the Milky Way nor Andromeda has ever been. There is a longer view still. The universe is expanding, and that expansion is accelerating. Dark energy, the poorly understood force driving that acceleration, is gradually pushing galaxy groups apart at an ever-increasing rate. Today, the Milky Way and Andromeda are close enough and massive enough that their mutual gravity overwhelms the expansion between them. But other galaxy groups further away are already receding faster than light can bridge the gap. Over trillions of years, more and more of the observable universe will slip beyond the cosmic horizon, still existing, but unreachable and invisible, carried away by the expansion of space itself. Milkdromeda will eventually become an island universe in the most literal sense, not because nothing else exists, but because nothing else will be visible. The galaxies that once filled deep field images, thousands of them stretching back to the edge of the observable universe, will have faded beyond detection, one by one, as the expansion carries them away. From within Milkdromeda, the night sky will contain only the stars of the merged galaxy itself, nothing beyond. The universe, as seen from the inside, will appear to contain a single galaxy surrounded by absolute darkness. Fred Adams and Greg Laughlin at the University of Michigan mapped the long-term future of the cosmos in a framework of successive eras. The stelliferous era, when stars still burn. The degenerate era, when only remnants remain. The black hole era. And finally, the dark era, when even black holes have evaporated. The Milky Way-Andromeda merger falls firmly within the stelliferous era. The universe is still young. Stars are still forming. Galaxies are still colliding. In the grand timeline of everything that will ever happen, this merger is an early chapter. Not the end of a story, but a moment in its opening act. And that, perhaps, is where to leave it. A blueshift, measured in a small observatory in Arizona in 1912 by an astronomer who did not yet know what he was looking at. A century of telescopes, spacecraft and simulations, each one confirming what Slipher's spectrograph first whispered, that something enormous is falling toward us across 2.5 million light-years of empty space. It will arrive. It will reshape everything. Not a single star will be touched. The universe builds quietly, and it builds on scales we were never meant to witness. But we measured the fall anyway, and in measuring it, we understood not just what is coming, but what a galaxy is, what it has survived, and what it will become when it meets the only thing in the sky that is not moving away. That faint smudge of light drifting closer in the dark. It has been falling toward us for billions of years, and we, without knowing it, have been falling toward it.